Good day, everyone. This is lecture 1.6 of Math 21. These are our objectives. We will recall how to obtain the inverse function of f or its graph given a one-to-one function f. We will recall properties of exponential and logarithmic functions to rewrite in a prescribed manner certain exponential or logarithmic expressions. At the end of this series of videos, students should also be able to evaluate inverse circular functions and to compute limits involving exponential, logarithmic, and inverse circular functions using their graphs. We begin by recalling properties of inverse functions. Suppose the composition f circle g of x is equal to x for all x in the domain of the inner function g, and that g circle f of x is equal to x for all x in the domain of the inner function f. Now, what does this mean? Okay. Here, x is the input for the function g. And when the output g of x is inputted to f, one recovers the original input x. Similarly for the second condition. Therefore, each function undoes what the other function does. Hence, in this case, f and g are called inverse functions of each other. And we write g equals f to a superscript of -1 and f equals g to a superscript of -1. And we read this as g is the inverse of f, or g equals f inverse. Similarly for this. For instance, consider f of x equals -2x plus 4 and g of x equals -1/2 x plus 2. These are linear functions whose domains are both equal to the set of real numbers. Now, one can easily verify that the composition f circle g of x, which in this case is equal to -2 times -1/2 x plus 2 plus 4, simplifies to x. Similarly, g circle f of x is always equal to x. Therefore, these two functions are inverse functions of each other. So we write f inverse of x equals -1/2 x plus 2. Similarly, g inverse of x equals -2x plus 4. Now we recall the graphical implications of two functions being inverses of each other. Note that if f and g are inverse functions of each other, then f sends a to b precisely when g sends b to a. Again, this is because each function undoes what the other function does. Therefore, a point with coordinates AB is on the graph of f precisely when the point with coordinates BA is on the graph of its inverse. So the coordinates are just interchanged. For instance, these are the graphs of our functions in the previous slide. The graph of f passes through the points 0, 4, and 2, 0. So its inverse passes through the points with the coordinates interchanged, 4, 0, and 0, 2. Now, a consequence of the interchanging of coordinates is that these graphs are just mirror images of each other with respect to the line with equation y equals x. And this is true in general. The graph of the inverse of f is the reflection of the graph of f about the line with equation y equals x. Please take note of this fact as we will use this later to obtain graphs of inverses of special classes of functions. Now, just a few remarks. A function does not always have an inverse function. Function f has an inverse only when it is one-to-one, or precisely when it is one-to-one, where a function is one-to-one when it satisfies the horizontal line test. That is, No horizontal line intersects its graph more than once. In other words, every horizontal line intersects its graph in at most one point. We also recall how to find the inverse of a function computationally. To do this, we just use the fact that the points on the graph of the inverse of a given function are obtained by interchanging the coordinates of the points on the graph of that given function. Thus, if our function is given by y equals f of x, then we may find its inverse by first interchanging x and y to obtain x equals f of y. Then, we solve for y in terms of x in order to get y equals f inverse of x. For example, let's try to find the inverse function of f of x equals 4x minus 1 over 2x plus 3. Okay, following these guidelines, first we write y equals 4x minus 1 over 2x plus 3. Then we interchange the roles of x and y to obtain x equals 4y minus 1 over 2y plus 3. And then we carry out the algebraic operations to solve for y in terms of x. We leave it up to you to verify that y equals 3x plus 1 over 4 minus 2x. Hence, f inverse of x equals 3x plus 1 over 4 minus 2x.